much for this kind introduction. I hope you all can hear me. So first of all, I would like to say good afternoon from Brazil. It's a great pleasure for me to be here. And also I want to express my gratitude for the organization of the Earth Day conference. For me, it's very exciting to be here sharing about my topic of research. As you can see, the name of the presentation is Space Farming Technologies from Space to Earth and from Earth to Space. In the next 15 minutes, my aim is to provide an overview about how we can utilize the concept of space technology transfer, not only to provide solutions here on Earth, but also how can us here on Earth can contribute to the future of space exploration. As you can see, this is the agenda of the presentation. I will start with a brief introduction about myself and why I'm here talking about space farming. This will lead me to present you the actual scenario of space farming, the challenges, technology breakthroughs, and how this is important for us to reach our long-term planetary sustainability. Well, about myself, once again, nice to meet you all. My name is Davi Souza. I am a Brazilian greenhouse specialist. My background is in electrical engineering, and I have been conducting research in space farming and doing some AgTech consulting activities for more than 6 years, specifically related to controlled environment agriculture. As you can see, and as it was mentioned, a bit of my professional pathway, everything started almost 6 years ago when I decided to prototype my first smart greenhouse, as you can see on the left figure, as a thesis of my electrotechnician course. This has led me to many exciting opportunities, such as becoming an electrical engineering intern at Pink Farms, which is the first vertical and urban farm in Brazil. And as it was mentioned, I went to Saudi Arabia to conduct research on advanced technologies such as organic photovoltaics in greenhouses, and also the development of small-scale experimental chambers for AgTech research, as you can see on the two right figures. And all of this is part of my mission, which is positively impacting people's lives with agriculture, space, technology, and innovation. That's why I am super excited to be here today talking about the topic of space farming technology. Now, moving to the topic itself, for us to reach the actual scenario of space farming, we must take into account that this is not a new topic. Space farming research started around the 60s with initial space missions together with the Salyut space station and the Mir space station. But what we have now, all of the efforts we put in along these years has led us to accomplish the operation of two very important plant growth systems right now at the International Space Station, which are FEAGRI and the Advanced Plant Habitat, or APH. But my focus won't be in talking more about the systems because my colleague Luke, which is the next speaker, he will be providing more details on how NASA is approaching them in the space farming research. What I want to mention here is that doing space farming research is not only about growing plants with the aim of scientific missions. The next endeavors of NASA will be on the development of the system called OHALO 3, which will be the first operational crop production system to provide information on productivity, reliability, and operations of the system at the International Space Station in microgravity, to apply this solution in future Mars transit vehicles, which are basically spacecrafts that will transport humans for other planetary bodies, such as Mars. At the same perspective, NASA is not only aiming the microgravity environment, but also they have recently announced a collaboration with a company called Spacelab on the development of LEAF Beta mission, which is the acronym for Lunar Effects on Agricultural Flora. And this mission has the aim to conduct a plant science experiment during NASA Artemis 3 mission on the surface of Moon. But together with all of this, I want also to mention that many efforts are being put here on Earth. Other institutions, researchers, and professionals are being putting efforts not only to address space farming itself, but also how this can be useful for us here on Earth. Some examples are listed are shown in the two right figures. The top one, you can see the Eden ISS, which is a project, which is basically a container farm project that operated in Antarctica for almost 5 years. And this project was held by the German Space Agency in collaboration with other space agencies around the world. On the bottom figure, you can see the biopod system, which is basically a biofarm that was developed by Interstellar Lab, a space company, and they are already conducting some testing of the prototype of the system and validating their commercial solution. But what this project has in common is that they are not only aiming to grow plants here on Earth, they also are focusing on how these systems, how these structures will be implemented in future space habitats, such as in the surface of Moon and then Mars. Now, moving to the challenges of growing plants in space. Let me tell you that since I have the engineering background, most of the topics that I'll be discussing here will be aiming at the engineering aspect of growing plants. That's why, let me tell you that if we are taking into account the challenges of growing plants in space, we must consider that this will directly affect the system's requirements, and this will be different depending on the space mission scenario. That's why it's very important for us, if we are looking on the plant perspective, to understand the interdependencies between the plant and the environment that these plants will be growing. This is what I call the plant-environment interface, or as it's common mentioned in the literature, the plant microclimate, which are basically all of the parameters that are interfering or that are affecting the boundary of the plant, such as the lighting, the climate, and the irrigation. And this will be very important if you are taking into account any plant growth system, no matter here on Earth or in space. But in the case of space, we must consider other external inputs that will be affecting this microclimate. And as you can see listed here, we have the space environment itself, such as the gravity, the radiation, and the pressure, which will be different if we are dealing with the International Space Station, with Moon and Mars. We also must consider resource limitation, stressors, biosafety, hardware limitations, or the technologies that we still do not have a lot of knowledge about them, and also the human-plant integration. And once we integrate these inputs with the plant microclimate, we also have the outputs associated to it, which is basically the photosynthetic activity of the plants, respiration, transpiration, physiological response, acclimation, adaptation of the plants to the space environment, biomass production, and also once we complete a growth cycle, we'll have a lot of data available to be analyzed and close the cycle of continuous improvement engineering. Now, let's talk about the technological breakthroughs that are allowing us not only to grow plants in space, but to make happen this revolution in agriculture, as was mentioned in the previous lecture. The first one is the LED lighting. Most of us are aware of the potential of this technology. This is a groundbreaking technology that is advancing a lot, not only the vertical farms, but this was crucial for the advancement of space exploration, or at least growing plants in space. But what I want to consider here, what I want to emphasize, is that if we are dealing with any artificial lighting system, we must take into account the light use efficiency, which is basically how much light we are providing to the plants and how these plants are utilizing these lights. And at the same time, how much energy is being put into this lighting system and how much biomass we are harvesting after the growth cycle. As was mentioned already here, I will quickly mention about this topic. We have a lot of research being conducted on the customization of the light receipts to reach optimal quality, quantity, duration, and uniformity. And this is well illustrated in the figures. But also it's important to highlight that we also have some barriers associated to the costs of LED lighting. Not only the purchase courses, which are basically related to the capex of the system, but also the energy consumption of the LED lightings, which is the main driver of higher costs in a vertical farm. And this is basically associated to the OPEX of these farms. Regarding this, I want to mention that we have really good forecasts or prospects about this technology based on the Hayes law. As you can see, we have a forecast on the light output per LED fixture or LED package as a function of cost and time. And as you can see in the beginning of this technology, we have higher costs associated to low light output of the technology. But we can expect after the years that this scenario will change. And this is the great opportunity on the LED lighting sector, because we now can start talking about LED lighting fixtures that can provide us higher light output with lower costs. Now, let's move to the other technological breakthroughs, which I was also mentioning in the previous presentation, which is the aeroponics. Basically, this is an alternative agriculture method without the use of soil. It basically, the system is composed, this aeroponic system is composed by the idea of delivering the nutrient solution to the roots of the plants with small droplets of water. And this is very relevant because it increases the contact surface between the roots and the water. It also provides root aeration and increase in water uptake. But another relevant factor of this type of systems is that we also need to provide efficient designed automated system to run a precise irrigation. And this is well exemplified on the figures. As you can see here, we have a well-known company called AeroFarm, which implemented the aeroponic solution in their vertical farms. But on the space side of the thing, we can mention another system that is also operating at the International Space Station, which is called X-Root. The system was developed by a space company called Sierra Space, and they're basically investigating the implementation or the performance of automated aeroponic systems in microgravity. And as you can see on the right figure, they are having really good outcomes related to it. Now, talking about the vertical farms, which was a topic already presented here, but I just want to mention that the idea of the vertical farms is to design growth systems that can maximize the use of space. And how to make this feasible? You must consider in the designing phase of the system how these systems can be modular and scalable. And this will also be based on artificial lighting and environmental control capabilities. One example in the space side of the thing, I want to present you the NASA's Biomass Production Chamber, or BPC. This is basically the first vertical farm, the vertical and technological farm ever, which was developed by NASA in the 90s with the aim to conduct space farming research. Just to summarize, as you can see in the figures, different views of the system. The figure B shows us the nutrient delivery system of the BPC. Figure A is the structure, which has a growth area of 20 square meters, and it is a structure with 7.5 high. And this has allowed us to know vertical farm as it is right now. And this is advancing even more. I just bring here one example on how the vertical farm approach can be implemented. It's not only about talking about just vertical layers that we can implement in a plant factory. We also can have different approaches for vertical farm. And the example of the container farms developed by Square Roots is a very great perspective of this. On the left figure, we have a container with vertical walls, growing plants in a vertical manner. But at the same time, there is an opportunity to stack these containers to have a huge farm providing more outcomes. And what is the benefits associated to it? What are the benefits? Basically, we can ensure a local food production and an enhanced food logistics for the food systems, the agri-food systems that we have here on Earth. Finally, the last technological breakthrough, I will mention about the controlled environment agriculture itself, or the controlled environment technologies, which are basically shaping the strategies on how we are implementing indoor farms. With that, we are advancing even more the knowledge on CEA systems architecture, and this is allowing us to cultivate plants in closed-loop systems. Together with that, we also have the opportunity to implement smart cultivation structures, providing environmental control, and allowing the system to perform the desired capabilities, which can be related to monitoring, automation or actuation, and all of these aiming the optimal plant growth. Some examples are provided in the figures. I just wanted to mention that they are very similar. If we see each one of these figures, we can see that they are very similar in the structure, in the design, but each one of them has a different purpose. From left to right, you can see an operational greenhouse in Antarctica. This is the example of Eden ISS. In the middle, the commercial biofarm module developed by Interstellar Lab. And on the right, a concept developed by NASA of a future space greenhouse. And what all of these solutions have in common? They can be implemented in space if we just adapt this inner structure to an external structure, such as a rocket module that will be delivered, that will be deployed in the surface of Moon and Mars. To conclude my presentation, we saw in this very brief overview about the technologies that we now have the opportunity to find ways to engage terrestrial agriculture with research, development, and innovation in space farming. But to make this feasible, to make this achievable, we must start thinking on how we can implement strategies for space technology transfer, and this should be done in an effective manner that can support current agricultural systems while reducing the negative impacts posed by climate change. And a very interesting initiative that I recently became aware is that some researchers are considering to add one more sustainable development goal, which is the space environment. Or in other words, how can we utilize the space exploration efforts to provide a long-term sustainable development in our planet? And this leads me to ask you, if you are interested to become part of this space endeavor, this human space endeavor, I want to make you a final invitation. If we are interested to know more about the topic of space farming, I want to briefly mention that I recently launched the SF101 course, which is the first online course in the topic of space farming. This is dedicated for space farmers, growers, and CEA professionals. You can see in the course real examples on space farming technologies with exclusive case studies. And the idea of this course is to teach you, or at least you will be able to learn how to use this knowledge in your favor, in your farm, here on Earth. So the SF101 is available on the Architecture Designer platform in the following link. And if you utilize the coupon of Space10, you can get a 10% of discount for 1 year access of the course. Thank you very much for the opportunity to be here. Thank you for your attention. I'm not sure if we have time for questions, but these are my contacts, my email, Instagram, and LinkedIn. Feel free to reach out if you want to discuss more about the topic or even addressing your questions. Thanks a lot.